Welcome, everyone, and thank you for joining us today. Our team, which includes Bissy and Cody and me, are excited to present our project on sentiment intelligence, which focuses on reading the voice of the customer at scale. We know that every modern business sits on a mountain of written feedback, from reviews and surveys to support tickets. The problem is that reading thousands of these reviews by hand simply doesn't scale, and a basic star rating never actually tells you why a customer is happy or upset. To solve this, we built and tested three deep learning models designed to read written reviews and automatically determine customer sentiment, allowing you to match the right AI tool to your specific business needs. With this presentation, we want to highlight what the system delivers for your business. To prove our approach works, we use 50,000 labeled reviews to build and test our system, condensing a task that would normally take a human team days into mere minutes. Our solution reads raw, free text reviews with no manual tagging required, outputting a clear, consistent positive or negative signal for all of your feedback. It learns the actual language of customer satisfaction rather than just looking for basic keywords, and it runs with the same reliability every time, regardless of your volume. We built this using the IMDb movie review dataset, which serves as a highly trusted, industry recognized benchmark so you can confidently trust our results. Now, let's talk about the data, where it comes from, and how we prepared it. We used an even split of positive and negative reviews written by real people. This balance is critical because if the model is fed mostly positive reviews, it can cheat by guessing positive every time and still get a high score. Because our data is balanced, you know that the accuracy of our model achieves comes from real learning, not a lucky bias. We then take this text and make it model ready through a tokenization process where we split each review into individual words and punctuation so the computer can begin to process it. This slide details how we build the vocabulary for the models. Computers can't read letters, so we have to translate your customer text into numbers. Our approach to this is directly grounded in formal natural language processing research, specifically following the original 2011 Stanford paper by Moss and colleagues that introduced this data set. Following their methodology, we built a 5,000 word vocabulary to keep the most useful language. To make sure the model trains efficiently, we encode each word into a number and pad the reviews so they are of equal length. During this vocabulary building phase, we made a decision to gather the top 5,050 words but completely throw away the 50 most common words in the data set. Words like the, a, and, or is are just background noise. They appear in every single review, whether it's positive or negative, and they tell us nothing about how a customer actually feels. If we kept them, they would dominate the vocabulary by sheer volume. By clearing out that noise, every slot in our 5,000 word vocabulary is reserved for words that actually carry a sentiment such as brilliant, boring, or waste. This ensures our models are focused on the language that signals whether a customer is happy or upset. And now Bissy will explain our model philosophy and architecture.
The models, what we built. We built three models. We built the fully connected network. Its strength is, being fast and simple and hard to stabilize. Its trade-off, it couldn't figure out not good and good not were not identical. The recurrent neural network, it understands sequences and phrasing, unlike the FCN, but it's not able to carry a running memory for long due to vanishing gradient that causes it to forget the start of long reviews. And then we have our third one, the biodirectional LSTM, that's purpose built for long text. It has gated memory, holds context across an entire review. It reads forwards and backwards to catch phrasing negation. The trade-off, it's the most complex and the slowest of the three to train. So here's just a reminder of the identical conditions for all of our models, except that we just changed the architecture.
Thank you, Bissy. Here's what the numbers showed, including one result we did not expect. This is accuracy on 25,000 reviews the model had never seen before. The simple baseline scored 86.3%, the RNN 83.7, and the LSTM, the one we expected to lead, 85.9. So the simple model scored the highest, but the gap over the LSTM is 0.4%, which is in a single run is within noise. I wouldn't call it more accurate. The fair read is that they're tied. And that's the interesting part. The simplest model matched the most complex one. So what did that complexity buy us? On accuracy, very little. On cost, a lot. The baseline trained in 1 minute 42 seconds. The LSTM took 8 minutes for the same result, nearly 5 times the compute for no gain. And that cost repeats every time you retrain. The RNN is the weakest option, slowest to train and lowest accuracy. Here are all three across 50 training passes. The baseline climbs fast and holds a steady line at the top, which is what you want to see in production. The RNN in orange is less stable and settles lowest. The LSTM finishes level with the baseline. The key point, three different designs converge on roughly the same number, around 86%. That means we've hit the ceiling of what this data supports. The limit is the data, not the model, and that shapes our recommendation. So what would we recommend? It depends on your data. We're matching the model to the problem, and all three are built and tested. For high volume and shorter text on budget, reviews, surveys, social posts, the FCN fits, and it's fast enough to score in real time. For longer text where context matters, support tickets, complaints, mixed sentiment, the LSTM is worth the cost. The RNN we keep as a control. We wouldn't deploy it, but it confirms our results are sound. The path we'd suggest is low risk and staged. Deploy the FCN first, best accuracy, lowest cost, and confirm the value before spending more. Then retrain your own feedback, which is where the accuracy improves past 86%. Move to the LSTM only where measurement justifies it, and expand the output from positive, negative into graded scores and topic tags like price, service, quality, so it can support real decisions. Lowest cost first, complexity only where the numbers support it. To summarize, the simplest model that works is usually the right one, and we attested that rather than just assuming it. That's the approach that we'll bring to your data. Thank you for watching.